object 50 centimeters away. So the object distance is given as 50 centimeters. DO is 50 centimeters. We know that the image has to be produced on the retina, and the average size of the human eyeball, or rather the distance from the lens to the retina, is 2 centimeters. So that is DI. So DO is 0.5 meter, DI is 2 centimeter, which is actually 0.0200 meter, which is this distance taken as 2 centimeter. And so we can find the power. The power is 1 by focal length. So, which is actually 1 by DO plus 1 by DI. So plug in the values and you get the answer. So on calculating this, you get the power as 52. What is the far point of a person whose eyes have a relaxed power of 50.5 diopter? Now the far point means the farthest distance to which the person can see. So the power is given, which means we can find the focal length. And once again, we know that DI is 2 centimeter and we're looking for DO. So the power is given, power is 1 by focal length. So that is 50.5 diopter. And we can again use 1 by DO plus 1 by DI is equal to 1 by F. And from there, rearrange to make 1 by DO the subject. We get that as 50.5 minus 1 by 0.02. So once you get 1 by DO, remember to take the reciprocal of that because we're looking for DO. So DO comes out to be 1 divided by 0.5, which is 2 meter. Near point of a person whose eyes have an accommodated power of 53.5 diopter. Now this is exactly similar to the last problem, except that now the eye is accommodated. That means it's trying to view something that's really close up front, and that's why we are finding the near point. Okay, and the problem is the same. We're trying to look for DO. We know DI is 2 centimeters, and the power is given. It's the reciprocal of the focal length. It's given as 53.5 diopter. Use the same formula, and I've already made 1 by DO the subject there. So 53.5 minus 1 by 0.0200 gives 3.5. And when you take the reciprocal of that, you get DO as 1 by 3.5, which is 0.286 meter. That is the near point of the person. In this question, a laser vision correction reshaping the cornea of a myopic patient reduces the power of his eye. So myopia, one of the reasons for myopia is the increased power of the lens. That's why the cornea is reshaped to reduce the power of his eye by 9 diopter with a plus or minus 5% uncertainty. What is the range of diopters? Okay, so here you just got to take 5% of 9 diopter. Now 5% means 5 by 100. So we take 5% of 9. That means you take 0.05. How do you get 0.05? 5 divided by 100 times 9, which gives us plus or minus 0.45. So it could be either plus 0.45 or minus 0.45. That means the range is double of 0.45. It's 0.45 multiplied by 2, which is 0.90 diopter. And the B part says was the person nearsighted or farsighted before the procedure? Actually, the answer is in the question. Myopia means nearsighted. So the person was nearsighted. And how do you know? Because we're reducing the power. When you reduce the power, that means the person was nearsighted. Okay? Because if the person is farsighted, then you increase the power of the lens. So in this case, it's very clear that the power is being reduced. And not only that, the question itself says the patient was myopic. So the answer is in the question. In this question, in a LASIK vision correction, the power of a patient's eye is increased by 3 diopter. Here we go. Here the power is being increased. That means the patient was not myopic, was not nearsighted, but was farsighted. Okay. Assuming this produces normal close vision, what was the patient's near point before the procedure? So you have to find the near point before the procedure. Okay. So we know one thing, that the near point is supposed to be 25 centimeters for a normal eye. And the patient or any person should be able to see all the way up to infinity. So when DO is infinity, the near point should be 25 centimeters. So let me show you what I mean. The power is 1 by F, and 1 by F is 1 by DO plus 1 by DI. So DO is 0.25. DI is 0.02, because when you hold an object 0.25 meters away, the person should be able to see it clearly. That means the image must be produced on the retina, which is 0.02 meters behind the lens. That means the power was supposed to be 54 diopter. That's for a normal eye. The problem says that the power was increased by 3, which means this person should have had a power of 51 diopter. That's why it's being increased by 3 to get it to 54. I hope that makes sense. So for normal vision, it's supposed to be 54 diopter, but this patient did not have a power of 54, had 3 diopter less, and that's why it's been increased. So the power in this case is 51 diopter. So now we can once again use the same idea, and we can find what his near point was. So we are looking for DO now, and I just made DO the subject directly, but you need to see what I did. Instead of writing 1 by DO, I just wrote DO is equal to P minus 1 by DI raised to -1. That means I'm already taking the reciprocal. So I'm doing it all in one step. We know that the power is 51, and DI, of course, DI is 2 centimeters, which is 0.02 meter, which gives 1.00 meter. This was the near point of the person. All right. Now the near point is 25 centimeter. So before this was done, the patient had to hold something 1 meter away in order to read it. But after the correction, the patient can now hold it 25 centimeters away, just like any normal person. Question 6. A very myopic man has a far point of 20 centimeter. What power contact lens will correct his distant vision? So this is a nearsighted person, a myopic person, and unfortunately the far point is only 20 centimeter. So anything beyond 20 centimeter, this person cannot see. That's his far point. So when he wears lenses, or when he wears a contact lens, he should be able to see up to infinity. That means when the object is at infinity, that contact lens should produce an image 20 centimeters away from his eye. Because his far point is 20, he can see anything clearly up to 20, correct? So what the contact lens does is, an object which is at infinite distance away, very far away, that contact lens, if it produces an image at 20 centimeter, then the person's eye lens can take it from there. I hope that makes sense. So DO is going to be infinity, and DI is going to be negative 20. Why negative 20? Because myopia is corrected using concave lenses, and concave lenses only produce a virtual image. So I have a diagram here to explain it. So that's the distant object. This is the image produced by the contact lens. Well, although this is not shown as a contact lens. Essentially, that image needs to be 20 centimeters from the eye so that this lens can take it on from there. So DO is infinity, DI is negative 20 because it's a virtual image, and then we can find the power of the lens. Now, it needs to be in meters, so 0.2, and 1 by infinity is 0. So when you do that, you get negative 5 diopter. Number 7, a myopic person sees that our contact lens prescription is negative 4 diopter. What is our far point? Once again, this is a myopic person. This time the power of the lens is given. It's negative 4 diopter. And we're trying to find out what her far point is. So that means how far away could this person have seen before wearing those lenses. So the person should be able to see all the way up to infinity, correct? The power is given. So from the power, we know the focal length, and power is 1 by DO plus 1 by DI. The person should be able to see up to infinity. So DO is infinity. And we're looking for DI. Where is this going to be produced? Wherever the image is, that would be the far point of the person. So 1 by infinity is 0 again. So we get power is 1 by DI, or DI is 1 by P. And 1 by negative 4 diopter gives negative 0.25 meter. So the far point is negative 0.25 meter, or negative 25 centimeter. In question 8, a microscope with an overall magnification of 800 has an objective that magnifies by 200. What is the magnification of the eyepiece? That's straightforward. We know that the total magnification of a compound microscope is the product of the magnifications of the objective and the eyepiece. And we're given the total magnification, the overall. So all we got to do is divide by magnification of the objective to get the magnification of the eyepiece as 4. And then the second part says if there are two other objectives that can be used with the same eyepiece, having magnifications of 100 and 400, what other total magnifications are possible? That's simple. So already we know the eyepiece has a magnification 4. If the objective has magnification 100, the overall is going to be 4 times 100, 400. And if the objective has magnification 400, it's going to be 4 times 400, 1600. Now here is a question that has multiple parts, but we will read it, do it part by part. An amoeba is 0.305 centimeter away from the 0.3 centimeter focal length objective lens of a microscope. So this is about a compound microscope, and we know a compound microscope has an objective lens and an eyepiece. So now we're talking about the objective. And the amoeba, which is the object, is 0.305 centimeter away. So that's DO. And the focal length of the objective is given. You have to find DI. So use 1 by DO plus 1 by DI is equal to 1 by F. and calculate. When you make di the subject directly, you can write it as 1 by FO minus 1 by DO raised to minus 1, which gives 1 by 0.3 minus 1 by 0.305. So that actually gives 0.183 is in meters, so it's actually 18.3 centimeter. Now the B part says, what is this magnification? Magnification is negative di by do. So it's minus 18.3 centimeter by 0.305 centimeter. And that gives you negative 60. So that is the magnification. In the C part it says, an eyepiece with a 2 centimeter focal length is placed 20 centimeters from the objective. So now the image distance was 18.3 centimeter from the objective. So that's the objective. The image is somewhere here, and the eyepiece is 20 centimeters away. So the distance from this image to the eyepiece is 20 minus 18.3. 20 minus 18.3. It produces an image here, and this is 20. So this is 20, this is 18.3, which means this is 20 minus 18.3, which is 1.7 centimeters. Now we know that the distance of the image from the eyepiece is 1.7 centimeters. So I'm going to call it DO prime. So DO prime is 1.7, and now again we got to find DI prime using the same formula. This time we use the focal length of the eyepiece, which is given as 2 centimeter. So 1.70 raised to negative 1 is equal to negative 11.3 centimeter. So that is the distance of the image from the eyepiece. And finally, what magnification is produced by the eyepiece? Again, use m is equal to negative di by do. We got the di prime, which is negative 11.3. Remember, two negatives make a positive. That's why there is no negative there. Divide by 1.70, which gives 6.67. Finally, what's the overall magnification? The overall magnification is the product of the individual magnifications of the objective and the eyepiece. And so minus 60 times 6.67 would give negative 400. So here is the last question. What is the angular magnification of a telescope that has a 100 centimeter focal length objective and a 2.50 centimeter focal length eyepiece? Now the magnification of a telescope is simple. It's negative FO by FE. So we're given both the focal lengths. So just use negative 100 centimeter by 2.50 centimeter. We get it as negative 40. And that is the answer.